All right. Neil just gave a great intro. He's ready to do it again.
No, I'm not. You can watch the recording.
Okay, done.
Oh, no, it won't. I've done it. Anyway, main point, this is about AI ML. So, why are we doing this? Well, I think it's fair to say probably most people in the room on the line have seen that probably about 5, 6, 7 years, there's been a lot more growth now in machine learning and AI. But there was that seminal moment in November of 2022 when ChatGPT came out, and I think there's seen now just a global increase in that, and that has certainly spurred on many of these CAE startups, where clearly a lot of the VC funds have seen how massive generative AI and AI is in the large language model space, and could this be true in the CAE space? And so I think it's quite an exciting time, and I'm sure I'm going to offend a company that I haven't got listed there, but I just thought of everyone I could see on my LinkedIn feed most of the time. So I put those down, but that's actually really exciting and good that there are new companies, just like we've seen yesterday, a number of startups with GPU native codes, which I think everybody would agree is a good thing in the sense that it's creating new energy in the sector. I think it's also a good thing that there is plenty of investment and realization from many of these sort of funding bodies that this is an emerging and interesting area. But I could imagine that for many people in the room here, it's also a little bit confusing when there's so many different options out there with so many different claims. How can you assess it? And to be fair, that is really the whole point of AutoCFD. It was to create a place where you could assess benchmark code, but as you've seen over the past few days, in a transparent and open way. I thought it was fantastic in Burkhardt's TFG that you had so many companies come up sharing openly results. But I think the way it works is because we're using test cases that are not their car. As soon as you're doing it on your own car, fair enough, there's a lot of sensitivities. But by using these open cases, I think you can see there's a lot you can learn even by sharing what previously you may have kept internally. And so really the idea for this TFG is, with so many new advances in machine learning and AI, can we establish some sort of benchmarks that you could test those methods, not in a super competitive way, but just to sort of understand where do we need to develop best practices and where do we need to continue to do research. Now, I think it is important to say that we're being a little bit biased probably when we say machine learning at the CFD. There are many different uses of machine learning that you could do for automotive CFD. You could try and improve a turbulence model. You could do something with the initialization. You could do something with the linear solvers. There are many, or transition models even. But I think it's fair to say that the greatest interest in the moment is with these sort of surrogate models. And so that's why we've taken a purposeful sort of focus on that area to begin with. But it's not to say that others are not important, but we just had to pick one. But Astrid, did you have any things you want to say just as a intro?
Yeah. I think just from my point of view, currently, it's just, I think it's not a question of whether this technology will come. It's rather the question of when and how we can prepare for this. And I think that actually then this is also in itself the motivation for this TFG to ensure that we as a community learn about these new technologies and upskill ourselves, and that we also learn about some of the pitfalls which this holds. And because I think that we will have to do a similar learning curve as for simulation as well. And so I will later on share also a little bit about different motivations, possible applications, and some of these learnings and possible pitfalls to look out for.
Like how to assess whether a method's good or not. Probably in the traditional CFD space, everyone knows the sort of metrics that you use, where I guess in the machine learning space, maybe it's not as well known. It's impossible to do a proper 101, but I appreciate that some people here will be very familiar with these methods and some people will be completely new. In the context of probably what we'll talk about in the next half an hour, in general, we're talking about some sort of surrogate model where you're taking, let's say in the case of graph neural net, the input being the CFD mesh and the simulation, typically the time averaged or steady state data, and then you're training just an input output where it can somehow link the geometry to the flow field or to the drag or to whatever. And then once it's trained, the idea is you can give it a new geometry or boundary condition that the model's never seen before. I guess one of the reasons that this is appealing is that given a suitable amount of training data, and suitable is obviously a pretty wide range I'm putting in here, let's say 25 to 500 cases, and you train it, again, just so much variability, 1 hour to 48 hours on a GPU, the key point is that typically in these methods, the prediction takes seconds, and it's the seconds bit that is obviously the most appealing. There is a lot of different approaches out there, whether you're trying to predict the full 3D volume field, whether it's just the surface data, whether it's 2D data, or just tabular data. But again, the main reason that this is of interest is because the prediction itself is orders of magnitude faster. And probably as many people know, there was always a desire for real-time CFD and the idea that GPUs could do that. I think it may be possible to do it, but the cost would also be quite high. So the wall time, maybe no, but you may need, a lot of compute to do that. Well, when we say the inference is order of seconds, it's also at a cost of, a cent or 2 cents. But I hope I'm speaking correctly when I say this, that most people accept that with current technologies, these will never replace high fidelity CFD. I don't think that's the conversation that most people are having. The question is, could they be an additional tool? That's not to say that they may not evolve to being better over time, but I would say that today that's where they should be. So I would be cautious in seeing this as some sort of, we're not going to do CFD. A bit like, to be fair, wind tunnel people really get annoyed when CFD people say, we're going to replace wind tunnels, where probably the reality is you're going to have wind tunnels for decades to come. I think an important note, though, is that in the world we live in, we're so familiar with these large language models, which are typically pre-trained. You don't need to train the model. You're just using the model, where at least with the current technology, most people here today will be training a model themselves. So the notion of just using one is a little bit different, at least with the current technologies in CFD compared to a ChatGPT or Bard or whatever model. Although there is definitely growing interest in these pre-trained models, but most likely you need a lot more data to do that. So it's not that it may not become like a ChatGPT style, but I think it's fair that at the moment it's typically a model you train with your own data. And talking about data, one of the things that we realized when we started to even consider doing a sort of AI thing is the data. And I think actually, to be fair, Astrid, you did the first one a couple of years ago where you just had to use data that you already had. And we realized that if we were to ask 10 companies to go and train a model, what data would they use? Some would have an unfair advantage by maybe having access to an OEM's data, which they privately have, but they can't publicly. And other people would try and generate their own, and it would be a mess. You wouldn't really be able to compare. It's also the case that in academia, there are almost no 3D full flow field automotive relevant data sets. When we started this 2 years ago, there literally were none in the public domain with a permissive license. I think the only things there were basically airfoils, 2D airfoils. That has changed a little bit since then, but it motivated us to, as part of AutoCFD, try and create public data sets that obviously have a very strong automotive reference, although they could be used to prove out just the, whether these could work for bluff body or just ML in general. And the key thing we wanted to do was then have a consistent data set that everybody could use and you could fairly compare methods. And the important principles that we had was that they would be fully open source and with a commercially viable license, which means the license on it should allow any of you with a commercial company to use the data and to develop a commercial product. You have to be careful. Many data sets out there are actually not, they're with an NC license, so non-commercial. So for many companies out there, that may scare your lawyers. Okay, so what are the data sets? Well, the first one is not technically linked to AutoCFD, but I think it's worth sharing because we all love the Ahmed Kabali, or not, depending on what investigation you've done. And this was something that in some ways was a quick test in a way to prepare for the next ones. I'm not sure how well you can see this, but essentially it's the Ahmed Kabali as standard, as everybody's done. It's about 20 million cells, this particular one, so it's purposely done as a slightly coarser one that would make it a little bit more appealing for academia, so about 20 million cells, but run for hopefully what people talk like 80 CTUs, time out, decent best practices for it. And you can see that this was done with a classic, Latin hypercube, where you look at the different geometries. As I'll show in a minute, there is a full paper describing all of this. So for the CD and the CL, you can see there's quite a distribution. There's very many different flow physics that you get between these different runs, so massive separation or quite slender separation. Everybody knows with the Ahmed Kabali, you can really have quite different flow fields, which makes it so difficult. But the thing that we did for these datasets, which is common for all three, is there is a consistent naming convention for every single dataset. So every dataset has a structure where for each run, you have the STL, you have the boundary VTP, so just the boundary files. You have the volume files, again, in a VTU or VTP format. You have the forces in a CSV file, and then you have the geometry parameters. And you also have images and 2D slices of the flow. And it's structured in a way that if you can work with one data set, you can probably just swap out the names to use the other data set, so it's meant to be quite consistent. And what I'd advise is there is a very long paper for this, which details exactly how to do it. There's also a website we created, and it goes into the full details. This is hosted on Amazon S3, but you don't need an AWS account to access it. It's free to download, and it's completely open source. So you literally just download this CLI, and you type it in, and you can download it. So there's no need for a username or a password or any link to it. And as you'll see in the next ones, there's been a huge amount of sort of team effort to build these sort of data sets. Okay, so now the AutoCFD sort of very specific ones. So we did the Windsor to match case one. And this was kindly done in collaboration with the Volcano platform guys. So we used their code, which was validated as part of the case one SRS noise factors to run this case. So we took a conscious decision, even though the computational cost was higher, to run all these data sets with either hybrid RANs or warm-up LES. We could have done RANs, but we were worried that we just couldn't get statistical convergence. We just couldn't converge solutions, basically. There's so many different shapes. And then your machine learning model would be learning not the geometry, but the error in your solver, essentially. So we wanted to take warm-up LES. So for this, we took a warm-up LES. It's about 280 to 300 million cells. Again, we took expense to run it out for longer than needed, I would say, probably about 80 CTUs. But one of the reasons we were keen to work with the Volcano guys is because it only needs one GPU. It's actually very good for large-scale database creation. So from a AWS point of view, only needing one node for each job makes it very easy to distribute jobs around. So this was, when people start talking about GPU native codes, I would say it's also very relevant for training data sets for AI, because if you're running 500 cases, any computational saving you can make on one obviously adds up a lot. So I think actually the growth of these fast CFD solvers will only accelerate because of the need to create more, trained data sets. Ashton did a great job in creating this parametric CAD model, and we're also providing the step files for this as well. So you have the STL and the step files. So if you wanted to be able to, adapt it yourself, there's about 355 variants of the geometry, and as you can see, you get very different flow fields. It's been dramatically changed to really try and test these machine learning models. That's quite large variation in shape. It's purposely done that way to make it just, not a super easy task to do. And you can see there's a very large then distribution of drag and lift. And in the paper, there's full details of all the different flow types. And even if you're not training a machine learning model, it may just be interesting to look at it from a flow physics point of view. Again, this probably looks very similar to the previous slide. You can see, again, the naming convention is very similar between all of these. So again, hopefully it should help. And it's all with open source file formats. So hopefully whatever code you're trying to do, and all of these things like BTK and STL, there's many libraries, open source libraries that can read them in machine learning methods. So PyVista, or in any of these things, you can easily now read in these VTK. So we didn't want to upload CGNS files because whilst you can read them in a sort of CFD code, you might not be able to open it up in a sort of an NL library. So that's why we picked the other ones. And again, there's a paper fully describing that. And this really was a sort of team effort because everyone's doing this a bit like AutoCFD as a sort of goodwill contribution. So the Volcano guys did a huge amount to help Astrid with the geometry modeling, and Gary obviously being the guru of the Windsor body, and then some help on the AWS side too. So now we have the DrivAerML, and there's a really nice paper. I mean, the upstream guys did a fantastic job of super detailed in the paper. I mean, I think it's like 80 pages. It is extremely detailed and includes all the validation of the methods. It's done hopefully so you can have full confidence in the data set. What this was a nice example of is trying to really build an automated workflow. And I'm hoping this is something that some of you may also take learnings from, and again, it's all explained in the paper. If you want to create your own trained data sets as a commercial company, let's say, that you don't want to make public, but you're just generating, I think we've learned a lot of things along the way of how to do this efficiently. So for example, in this, we worked quite closely with Burkhard and Vangelis and his team to start with the answer mesh. Mesh and geometry, and the geometry is morphed, and then there's a consistent volume meshing in answer. So every single case is meshed in the same way, and then that spits out into the open form, and then it goes through the upstream process. And in 1 second, and it has consistent post-processing. It spits out everything, all the cases, all the VTPs, the VTKs, the statistics. You can see some of the morphing of the geometry. So this was again guided by Burkhard, and some of the, wanted to make sure this was relevant as well. You saw the Windsor was more of an academic way of doing it in a way. Let's just go crazy with the shapes, which is good. This in some ways is a more nuanced, slightly more nuanced changes. It's not as big changes, but it's probably more relevant for an automotive company. But one of the things in the discussion I think we had just earlier about runtime and how long to average for, when you're running 500 simulations, one approach, which is still valid, is to say, I'm just going to pick the longest they need to run for and run for that. And that's the sort of safe option. But the other approach is to use things like the mean calc, where for every single simulation, we have a set tolerance. And so some simulations would run out, let's say 4 seconds, some for 3, some for 5. but there would be a consistent, and you can see with these graphs, it's all in the paper, that each case ultimately ended up needing a slightly different running time, but it was all done automatically. And that was quite nice because I think it also saved us quite a lot computationally because each case was only running for as long as it needed to run for. And again, quite a large spread. So this was done again with a Latin hypercube, like a DOE, to make sure that we could expand the data set as well if we wanted to. And what's interesting with this, at least I always find this interesting, probably the people in the automotive will be used to this, but you see quite large changes in drag as well for relatively minor changes in the geometry. So this is one of these ones where it's by just eye, you wouldn't know, you wouldn't think that there would be such a big drag. The other thing that we did with the data set is we purposely put out, for example, constant ref and normal. So we have some forces where we keep a constant reference area, and we have some where we actually calculate the frontal area for every single geometry and expose that. So we tried to give as much data depending on how you want to do the simulations. And again, there's a full paper here that fully sets out in detail, because I think depending on the method that you have, you may want to really know what's going on with how the case was solved, what was the boundary conditions, what was everything. Others, you may just need to take the STL or the VTP and be fine with it. And again, this was a huge collaborative effort. The upstream guys did an amazing job to build out this whole workflow. And one of the key things we wanted to do was to validate it. If you're going to run that many cases, we want to make sure you could have faith that the hybrid round setup, that the time step, the averaging was all done in a consistent way, so that as much as possible, your machine learning model is learning the difference between the geometries and the flow, and not, that one didn't converge and one did converge, which could easily be the case if they were all done with RANDs without any form of sort of careful tuning to it. It was also it was a lot of work by the beta CE folk to also create the automating and the meshing. And if you try and mesh 500 cases and spit everything out in the right way, it's a lot. And Burkhardt helped to make sure that this was relevant, hopefully, for the automotive. Just in terms of the data, I think this data set is between 30 and 40 terabytes, something like that. So it's quite a lot of data. So there's also a lot of lessons, and I'm sure you could speak to us individually. There's a lot of lessons we learned along the way of like how to run cases and how to automatically get messages if a case failed, and how to move the data around. And yeah, there's lots of interesting stuff. Some of it's in the paper, and some of it you may be able to just get. But yeah, big thanks to everybody on that. Now, with all of that, what we were hoping is we'd have 10 presentations from all the wonderful AI/ML startups out there who would be so eager to share the results. I'm kind of joking a little bit there. I mean, we're not stupid. We completely understand that with the methods being so new, there is a sense to make sure that you're only showing the results that you can really be proud of and being careful of. So the positives, I think, is we did have a good number of active participants in the TFG sessions. I think it was good that we created these data sets. They took us a lot longer than we thought they would, which we probably should have realized. So one of the reasons that probably people struggled is we'd hoped to give this data, 9 months before, but in fact, it was probably only about 3 months before. So it just took so long to get everything working and getting, the approvals to release it, to open source it, many factors that complicated things. But of course, yeah, the negative was, we did get some abstracts, and unfortunately they, were pulled, and we came down to essentially just having Astrid and I, who are now representing the surrogate modeling bit. We have Tonji, who's doing on machine learning perturbance modeling, but for the actual surrogate bit. And I think we had sort of limited academic participation. I was kind of hoping we may have seen more universities. But I think maybe the data sets were so big and the meshes are so big that it's probably hard for an academic group to, where do you find space for 20 terabytes? Most people's quotas on their systems are not 20 terabytes, so we probably focused a bit too much on the automotive OEM use case and maybe a little bit less. But we can easily make coarser versions of these data sets. So there is options to do it.
And maybe just to mention, I mean, these data sets are super huge, but I mean, Neil put it in a really nice way on S3 so that the data can be pulled in a very automated manner. So it's actually no issue to just pull data set one by one, do some processing, then release it. So because my quota is just like 500 GB.
That's true. The decision to put it in a run-based format, not zipping it up, for example, means that you can just download one run and a subset of one run, and you could, I think, you can download it, do some processing, and then delete it, and then download the next. So there was some thought of the sort of data structure. But I think we just wanted to say that, it's a bit tongue-in-cheek. We do appreciate that any new startups companies has to protect their IP, and there's always a sense of oversharing, and they want to show their best possible results. But I would hope, and maybe this is where some of the people here in the room can give some reassurance, that just as many of the large ISVs have come up on stage and shown how some of their methods fail, I think people in the audience respect that, actually, and don't say, you're terrible, we're not going to use you. There's a certain transparency that I think is welcome. So I think what we're saying is, please use these data sets, and maybe even beginning just internally, privately. Fair enough if you don't want to publicly talk about them, but perhaps through working with one of the automotive companies here, you may be able to just use them and see, build up confidence, and maybe by the time we get to the next workshop, there'll be a little bit more maturity and comfortable to share. And then hopefully all the people here can then, just as we've had a great discussion about the difficulties with CFD methods, we can have the same about AI/ML. You can download them. I know people have been downloading them, so that's good because we've had messages, of feedback, which is great. We haven't fully actually planned out anything for AutoCFD5, but I think it's pretty certain that these data sets will be used in some way for it. So there's plenty of time now to start sort of learning at it. And we've created a website, at least you can log on and sort of follow the publications and any updates to the data sets. Astrid, did you do any final thoughts?
No, I will share my final thoughts then later in my presentation.
All right.